Hello guys, so welcome back to our lecture 16. This is the third part in which we're gonna discuss another important, criteria for the BJT transistor, which is basically the BJT currents. So the BJT transistor has three terminals: base, emitter, collector. Okay, and basically each one of those has its own current. I mean, there is IC current that we discussed or touched base, in our last video. The current that just go through the collector and then collected by, VCE battery. There is also a base current that comes from the base and an emitter current. Okay, and we're gonna discuss today the nature of each of how this basically currents constructed in the structure of the transistor itself. And to discuss that, we must go back to our basic operation of the transistor, which is basically the active region or the saturation region, because basically the characteristics of these currents really depend on the region of operation, either active or saturation. So let's start by the active region. So this is basically from the last lecture. I just copied and pasted here this structure here. We said that G1 is forward. So this guy is forward here. And G2 is off. It can be reverse, it can be, on, but less than 0.4. The junction voltage is less than 0.4, so it can be considered off. And here is forward and on. It must be on. Okay. So we said that there will be, since the emitter is heavily doped, there will be more electrons moving from the emitter to the base, rather bigger than or greater than the number of holes that goes from the base to the emitter. And we said that G2 is off. There is no, charge exchange between the base and the collector. So basically, this situation is like we are injecting electrons into a reverse junction or off junction, which is basically G2. So this injected electrons will just flow because there is, a positive, terminal here of the VCE battery. That's good. Good. Since we have a moving charges, electrons and holes, so we have currents. We explored IC. We said that IC is basically these currents, these electrons. Okay, see these electrons going from the base to the collector, so the direction of the current is basically down. So like this. Well, this is IC. So IC should be like this. Opposite to the direction of the electrons. This is, conventional way of describing the current. The current of the electrons is basically opposite to the direction of the electrons. Good. How about this holes here? So there is I holes. So basically IC, guys, is basically the current of the electrons. Okay, I. How about this I hole current? Since there are holes, although they are small, we said that since the emitter is heavily doped, so maybe for each 100 electron that moves from the emitter to the base, there is just one hole that moves from the base to the emitter. So there is also I hole here, which is a current due to positive charge, and this current have the same direction of the holes because its holes are positive. Okay, so basically what's gonna happen is that this guy will move like this. It should be injected from the base. So this will be, the direction of this whole current. And so this I base here that's going into the base, like the collector current, it's going into the collector. Both are going into their terminals, either the collector or base. Okay, will be basically this whole current. How about IE? That's now Kirchhoff. You know, it's really simple. Look, now, this we have here, this, let's do it with red or green, or green. So these electrons make IC. I'm sorry. Yeah, direction is down. And these holes make IB. So let's no, it's just also with green. So we have also IB like this. So in the emitter regions, there are two currents now. There is IC and there is IB. And both are going down. So they will be basically, you know, combined at that terminal. So here there is current equal IE, which is basically now going out of the emitter, just to Kirchhoff. IE is equal to IB plus IC. You know, this is physics, Kirchhoff, and also, you know, I'm sorry, this is physics and also Kirchhoff. I mean, they should be matched, of course. Okay, so we see that without even knowing that there is something called the Kirchhoff current law, we see that IC and IB are just combined in the emitter region. So they will construct basically IE, and I should be going out of the emitter. Okay, because this is a combined current, okay, from IC and IB. So let's summarize what we have said. So I hole, or the whole positive current is basically IB, and IE is basically IB plus IC. What else we have? So another important observation is that IC and IB are both junction current, and basically the same junction. Okay, same junction current. So they are basically proportional to each other. I mean, if we increase the forward voltage of this, so if we, let's say this, so if we increase the forward voltage of the junction, G1 basically, VBE is the G1 junction. If we increase this VBE, basically both will increase. IC will increase and the IB will increase. And both should be increased by the same ratio. I mean, same percentage. I mean, if IC increased the 10%, IB should also increase 10%. So they are basically proportional to each other. So IC or IB, whatever, is proportional to the other guy. If we said IC is proportional to, so it will be proportional to IB. If we say IB, if we start by IB, so IB is proportional to IC. And actually both are dependent. Dependent on what? Dependent on VBE, okay, the junction voltage, okay. And for each transistor, when we fabricate the transistor, there is usually, you know, one ratio for this, which is called beta. So IC equal to beta IB. And remember, guys, from our last recording, we said that the emitter is heavily doped. So maybe for 100 electron move from emitter to base, there is one hole moving from base to emitter. This is basically beta. So this 101, this is basically beta. So beta here usually is from 50 to 200. If you say 200, you can say that for each 200 electron move from emitter to base, there is one hole moving from base to emitter. That's basically beta. This 100, this basically percentage that I said is just beta. Okay, so in the active region, IE is equal to IB plus IC. IB and IC are going, IB is going into the base, IC is going into the collector, IE is going out of, the emitter. And that's why the NBN transistor has such a symbol. base, collector, emitter. Okay, and the arrow here is going out. Why? Because basically IE is here, going out of the emitter. IB is here, IC is here. Okay. And let's continue. So basically in the active region as well, VBE we know it's 0.7. Okay, and the junction or VBC should be less than 0.4. Just to continue the picture about the active regions. Also, we are studying the current, but we see that the currents IC, IB, IE are basically dependent on the region of operation. The characteristics, I mean, the relations that connect these currents together. Good. And of course, you know, just to complete the picture, VCE, okay, is equal to VBE minus VBC. Okay, and it should be greater than 0.3. Okay. Now let's talk about the, you know, saturation, the current in the saturation region. How the currents behave in the saturation region, because basically now one of the junctions become forward. So, and on. So J1 now is forward and on, just like the active region, but now G2 change it. So let's do that with, with another color, just to show the differences. So let's do that with this color, for example. So now G2 is forward, not just forward, and on. It was off in the beginning, now it's on. So what is that? What is that change? Will it change in our, you know, currents? Basically now G2 is forward and on, so there will be a charge exchange between the base and the collector. So there will be holes moving from the base to the emitter, and there will be basically electrons moving from the from the collector. I'm sorry, in the beginning there will be holes moving from base to collector. Okay, and now there will be also electrons moves from the collector to the base. Okay. And now look at IC. There will be changes as well. Okay. So let's go back to the active region to show something. So in the active region, we said that IC is equal to beta IB. So basically, beta equal to IC over IB. The same relation. Okay. How about here? So IC over, let's examine this relation now. In the active region, the relation is this ratio is constant, equal to beta. Whatever we have an increase in IC, we will have the same increase with the same percentage in IB, so the ratio is basically constant. How about now in saturation? Let's see. So IB is going into the base, so there is no problem that this IB basically will be just branched into you know, two ways. So one branch or one portion will go down and another portion will go up. Okay, so basically IB is equal to I holes, and this hole is this I hole is basically from base to emitter, plus another hole current from base to collector. So IB increased. Oh, the denominator now increased. How about the numerator? I see. Let's check. So this guy I see. Let's do that to another current. I know it's messy now, but let's see. Look, IC is electron current. Okay, basically. So you have electrons moving in that way, those guys moving from let's base, I'm sorry, emitter, base, collector. This is IE1, whatever, IE, okay, 1. And you have now another electron current. In the other, I mean, there are electrons moving from down to up, emitter, base, collector, and there are electrons move from collector, base, emitter, collector, base, emitter. In the other way, IE2. So IC now is basically the subtraction between them. Okay, so IC is equal to IE1 minus IE2. And IE1 will be basically greater than IE2 and I electrons too. And the reason for that, because the emitter is heavily doped than any other region. It's heavily doped than the base and heavily doped than the collector. So the amount of electrons that are injected from emitter to base is bigger than or greater than the amount of electrons that are injected from the collector to the base. Okay, so still IC have the same direction. It's going into the collector and still in that way, but it decreased now. Look, in the beginning it was IE1 only. It was only the electrons that move from emitter to up the way to the collector. Now there are, there is subtracted part. Okay, so the numerator decreased and the denominator increased. So basically this ratio is less than beta now, less than or equal to. Again, why equal to? Because again we have a transition point. Okay, this transition point belongs to both sides. And to make you remember, if we remember the characteristics between IC and VCE, we said that at point 3 we will have this transition. So after point 3 the collector current is constant and this is the active region, and then before point 3 it is linear. Point 3 is here is saturation, here is active, this is a transition point. Okay, transition point. Okay, good. So now IC doesn't equal to beta IB. IC now is less than, we can write this is another way, that IC is less than or equal to beta IB. It will be equal to beta IB in the active region. When you go to saturation, it will be less than this. But still, this is IB, this is IC, still IE is the addition of both. It's still IE, so this is number equation 1 or whatever. Relation 2 is still IE equal to IC plus IB. Still that. And again, to make the the picture complete for the saturation region, VBE 0.7, but some books assume it's 0.8. And that's fine. I mean, this is just rule of thumbs, and both are very close to each other. Okay, and basically 0.7 and 0.8 are basically both are approximations. Okay, as you will see in the lab, it's not basically exactly 0.7. It might be less or might be higher. Okay, and VBC should be greater than 0.4. Okay, because G2 is forward and on now. And the VCE will be less than or equal to 0.3. Sometimes it's assumed constant equal to 0.2. So there are many, I mean, the VCE in the saturation region, hardly change. It's a change in VCE will be very small. So usually when we analyze circuits and we know the transistor is working in saturation region, we assume that VCE is 0.2. Just it should be something less than 0.3. Okay, so we take always a kind of averaging. So we assume it may be 0.1, it may be 0.50, 0.15, it may be 0.05, it may be 0.3, it may be 0.25, whatever. So we usually assume it's 0.2. Okay. So again, to summarize what we have started, we were discussing the current in a BJT transistor, especially NBN. Okay, this was our study case. We found that there are three currents, i.e., the current out of the emitter point or the emitter terminal, IB, the current going into the base terminal, IC, the current going into the collector terminal. We find that IE is all the time in active region or saturation region equal to IC plus IB. We find that in active region IC is equal to beta IB, okay, and beta is a characteristic for the transistor. When you buy a transistor whose beta is 100, beta is constant, a parameter. And in saturation region, no, IC over IB will be less than beta. Okay, and of course, G2 here will be off. The junction between the base and the collector will be off. And in the active region, this junction will be, in the saturation will be on. And in this junction, G2 between base and the emitter will be, base and the collector will be off in the active region. Okay, guys, this is basically, an overview for the currents of the BJT and also the basic differences between the active region and saturation region. And this will be basically our key in order to start analyzing circuits for the transistor. Thank you very much for watching this video and see you in the next video. Bye-bye.